dense matrix algorithms. So in parallel computing, matrix algorithms are particularly important because they can be divided into smaller tasks which can be handled simultaneously as well as readily. So due to their regular structure, parallel computation involving matrix and vectors really lend themselves to data decomposition. And typical algorithms rely on input, output, or intermediate data decompositions. And most algorithms use one or two 2D blocks cyclic and block cyclic partitioning. So the first algorithm which we will study right now is matrix vector multiplication. So in matrix vector multiplication, we aim to multiply a dense n cross n matrix A with an n cross 1 vector x to yield n cross 1 vector y, and it requires an n square multiplication additions and multiplications and additions. And there are two types of matrix vector multiplication. So the first type is row wise 1D partitioning, and the second type is row wise 2D partitioning. So in row wise 1D partitioning, the n square n matrix is partitioned among n processors, where each processor stores the complete row of the matrix, and the n cross 1 vector x is distributed such that each processor owns one of its elements. So we will study this in the next diagram. So here this 1D row wise 1D partitioning is divided into 4 steps. This first, the second, third, and fourth. So in the first step, the matrix is divided into n processors, where each processor stores the complete row of the matrix. Like in this, we have divided this matrix into this n rows, and each row is allocated to a single processor. And vector x also is divided in such that each element of vector x is belongs to the row of the matrix. So here we have seen in this. So the second step is all-to-all broadcasting. So in all-to-all broadcasting, each processor has its own vector x. So this vector x will get copied to each processor P0, P1 up to Pn minus 1. And in the third step, there will be a computation process which will going on, and here each row of the matrix will get multiplied with the vector x. And in the fourth step, the resultant vector is created. So since each process starts with only one element of x, and all-to-all broadcast is required to distribute all the elements to all the processes. And here we will use this algorithm to compute the resultant matrix, and the all-to-all broadcast and the computation of yi both take O n time. Therefore, the parallel time is O of n. So in this, a series of multiplication and addition is going on, and in this we have seen that each processor performs an operation to multiply the row with the elements of x, and this process happens simultaneously. That is why the parallel time is O of n. So our second type is 2D partitioning. So in 2D partitioning, the n square n matrix is partitioned among n square processors, such that each processor owns a single element. So in this, there will be n square processors, and in 1D partitioning, we have used n processor per row. So in this, the n cross 1 vector x is distributed only in the last column of n processors. So we will now study it with the diagram. So it is the diagram of 2D partitioning. So in this, the first step is one-to-one communication. So in one-to-one communication, all the vector x along the principal diagonal of the all the vector x will be allocated to principal diagonal of the matrix. So all the processor which belongs to this diagonal of the matrix, they will be allocated to the vector x. So in the first step, this will going on, and in the second step, there will be one-to-all broadcast. So in one-to-all broadcast, it copies the vector elements from each diagonal process to all the processes in the corresponding column using n simulation broadcast among all the processors in the column. So in this, the vector x gets distributed to each of the column like this. And in the third step, there will be all-to-one reduction. So as you are seeing, the arrows are going from left to right in this. So it means that the computation process is going on over here, and the resultant elements get stored in the last row of last column of the matrix. And in the fourth step, the resultant vector is created. So so I have explained this in these steps, and there are three basic communication operations which are used in this algorithm: one-to-one communication to align the vector along the main diagonal, one-to-all broadcast of each vector element among n square n processes of each column, and all-to-one reduction in each row. So in this, each operation takes O of log n time, and the parallel time is O of log n. So the cost of operation will be O of n square log n, as we are performing operation for the n square element. So the time complexity will be O of n square log n. Hence, this algorithm is not cost optimal. But there are certain kinds of benefits which we will get from 2D partitioning. Like for large scale parallel computing, 2D partitioning is far superior in efficiency, scalability, and communication. While for small scale problems for or few processors, 1D partitioning is easier and sufficient. Now my friend will be going to present for matrix multiplication.
Good morning, ma'am. I'll be talking about matrix multiplication and how we can make it faster using Cannon algorithm. If we have two square matrices A and B, multiplying them gives us a new matrix C that is equals to A into B. The basic way to do this takes very long, especially when the matrices are very large, and multiplying the used tables takes a lot of work and time. To speed this up, we can break the matrices into small parts of n cross n matrix, where we have q into q array blocks of Aij. Next slide. Consider two n cross n matrices A and B partitioned into p blocks Aij and Bij of size n by p root p and n by root p. Instead of one person doing all the math, we split the work amongst multiple people. At the end, we put all the parts together to get the full result, just like solving a giant puzzle. Computing submatrices Cij requires all submatrices Aik and Bik. After that, we perform all-to-all broadcast of A along rows and B along columns. Next. In this algorithm, we schedule the computations of processes of the ith row such that at a given time, each process is using a different block ij by basically using shifting processes. These blocks can be systematically rotated among the processes after every submatrix multiplication of every process gets a fresh Aik after each rotation. So ma'am, basically here what happened is, in the first matrix we do left shift in each row, and in the second matrix we do upshift in each column. After the first initial alignment is done, we do single shift left shift in A matrix and upshift in the B matrix to generate the first shift, second shift, and the third shift. After the last third shift, we do a total of n by p root p shifts till we get the resultant C matrix. The steps are explained. Align the block of A and B in such a way that each process multiplies its local matrices. It is done by shifting all submatrices Aij to the left and all submatrices Bij in j steps. Cannon algorithm is the one we have used here. It is a very smart way of organizing teamwork in matrix multiplication. Imagine that each processor moves data in a structured way to avoid waiting and ensure smooth calculations. Each block of A moves one step left and each block of B moves one step up. Performing the next block multiplication add to initial result, repeat until all root P blocks have been multiplied. In conclusion, we can say that matrix multiplication is computationally expensive, but using block-based parallel and techniques like Cannon, we can significantly improve efficiency. Canal algorithm ensures structured data movement, minimizes communication overhead, and enables scalable parallel matrix multiplication.